you have just covered some of the most important and tricky bits of doing data analysis using R. So we just finished up with the issues of using a continuous outcome variable and a categorical predictor variable using analysis of variance, or more specifically what is known as a one-way analysis of variance. So now it is time that we do a little bit more tricky bit. So you knew that if your predictor variable is continuous or a mix of continuous and categorical, then you could use a multilinear regression, but the name of that was analysis of covariance, right? In this particular situation, we have got one continuously distributed outcome variable, but now you have got two or more than two predictor variables, each of which is a categorical variable. It's not very difficult to understand. Say, for example, if you've got men and women and you give them placebo versus drug, what would be the recovery time? Is it going to be different for men, the recovery time? Is it going to be different, the same for men and women? We can add even more if we keep in mind what would be the case with different ethnicity, for example. Does it vary by ethnicity, by gender, by the placebo versus the drug? How do we model those things? This is the objective of learning about the two-way ANOVA, where one outcome variable, but more than one categorically distributed predictor or explanatory variables. Let's see how do we do this.
I'm going to introduce you to the concepts of two-way analysis of variance. Okay. Two-way analysis of variance, which is kind of to be shaped after one-way analysis of variance. So while we will be while we have already discussed how to conduct one-way ANOVA and two-way ANOVA, we're going to have two such categorical variables, two or more such categorical variables, and we'll learn from them that experience. One of the important aspects of using a two-way ANOVA is this, that it enables us to study interaction effects of two variables like this. So say, for example, we are interested to find out different country types and breast cancer rates on these countries and their economy types. So we could actually perform this based on whether there are some interactions that are taking place, whether there's a parallel interaction, or whether the lines are parallel, or whether the lines are going to cross each other. Those are the kinds of things that are very, very important when we start looking at this. Sometimes it is useful to take the plot, and then from the plot you can infer what kind of analysis you're going to conduct. So to repeat, in two-way ANOVA, we are going to extend one-way ANOVA, and we're going to include two or more factors. As we have already mentioned, that in the context of R for statistics, we have seen that any categorical variable can be converted into a factor variable. So the way to do that is you take a categorical variable, which usually contains a number of categories, and you include a function called as factor, and then if you add the variable name of that particular categorical variable, then that categorical variable will be converted into a factor level variable. We have also seen that it is quite possible for you to convert a continuous variable to a categorical variable. That is, if you use the function cut and then introduce breaks in that continuous variable where the breakpoints will occur, then you can convert a continuous variable into a categorical variable. And then you can use the function as.factor that will convert the categorical variable into a factor level variable. And then each of the levels of the categorical variable, that is, each of the categories of the categorical variable, will then be the levels of the factors. Another thing that we noted when we were discussing one-way ANOVA is that R, when R uses a categorical variable or a factor level variable, R uses the individual factors in that factor variable or individual levels of that factor in the factor variable. Those factors are organized on the basis of their alphabetical occurrence. This needs a little bit of an elaboration. Say, for example, you have developed a factor variable, say, let's say you took a factor variable gender, for example. Take a factor variable such as gender. You can use factor variable as gender either as male, female, or boy and girl. Now, if you use a factor variable as male, female, then the category female will be awarded or assigned a value of 0, and the category male will be assigned a value of 1. Why? Because females starting with F occur first in the alphabetical order, then males that occur later in the alphabetical order. So females will be assigned a score of 0 and males will be assigned a score of 1. On the other hand, if you took the same variable gender, but had its two levels as boys and girls, then boys will be assigned a score of 0 and the girls will be assigned a score of 1. This factor needs to be taken into consideration when you use a categorical variable in an ANOVA setting, in either one-way ANOVA or two-way ANOVA setting. This tells you that it is quite possible for you to reverse the categorical order if you are prepared to change the name of the factors or the levels in the factor so that you can tweak their alphabetical order. So it requires a little bit of imagination or maybe some sort of a smart text-based tweaking so that you can manipulate R to present what you want out of it. So this is a factor that you need to keep in mind when you want R to understand the creation of dummy variables, for example. But this also works in case of working with factor level variables at every stage. So suppose we have two factors. One factor A has got I levels, I number of levels. So consider I to be like 3 levels of factor. Or B has got J levels. So let's put J to be 2 levels, 2. Therefore, for n individuals in a sample of data, the kth individual, let's say we take about 100 individuals, so n is 100. And let's say we are talking about the 5th individual, so the kth individual is like the 5th individual. That person will have a notification of I, J, K. So if you're talking about the ith level for factor A and jth level of factor B, then the person who occurs in that kth order of the n will have a notation for that particular person. That person's position in the graphic or in the two-dimensional matrix of data will be like n underscore ijk. Okay? And if that individual is also measured on the continuous variable of interest, let's say the y variable of interest, because we are talking here in terms of a continuous variable which is regressed on a kind of on other categorical variables. So his y variable is a continuous variable and just one variable, whereas with the A, you can have any number of categories. Maybe let's say in our example of length of stay. So let's say we are going to study length of stay of 100 individuals at a particular hospital or a group of hospitals. And then we are comparing gender with department, let's say, for example, or socioeconomic status with department. Then yijk could be the length of stay of the kth individual measured on the ith level of, say, socioeconomic status. Let's say socioeconomic status has got 3 levels: very low, medium, and very high socioeconomic status. And for example, the department, let's say we've got like 3 departments. So for example, medical department, surgical department, gynecological department, and then we want to combine the two together. So what happens is we can have a possible combination of 9 subtypes. So this person will have Y, length of stay, IJK, with an overall mean. That is, if all of these were kind of set off at their baseline level, we would still see that there would be some sort of a notion of a length of stay, right? So that's the mean that we can expect. And then there would be some effect that is entirely because of the variability that you can expect because of the specific ith level of the A variable. And then for I and J combination of A and B variable, because remember that A has got I number of categories, B has got J number of categories. Therefore, AB, when we put them together in an interaction term, it will have I times J number of categories. And that is represented here by AB underscore IJ. And then, in addition to what would be some sort of an overall population mean, effect because of the individual category of the variable A and individual category of the variable B, and interaction of A times B, that is I times J categories, it is also going to have an error term, and that error term is unique to the individual to whom this study is going to belong to. And because we are here dealing with a linear model situation, that's how the linearity of it is going to work. So using the Wilkinson-Rogers formula, we can actually have a Y variable, that is the length of stay variable, that can be regressed on each of these 3 layers of the explanatory variable. So that makes really a lot of intuitive sense. So we'll say that there is an overall intercept kind of situation, which is given by the mean of the population that we expect. And then each of the individual categorical variable situation that we can get out of this. So thus, in this way, we can put everything into the larger paradigm or the larger framework of a linear model and can still work with R. And certainly that's the way R works very, very easily. So this is what we're going to model using R. Nothing esoteric, nothing peculiar. We're just going to have an additive effect and a multiplicative effect. And as we have seen, that there are various ways in which we can evaluate them. So that's the principle. The most interesting thing in terms of using the two-way analysis of variance here is this, that you can use what is known as an interaction term that is very useful. So let's go and take a look at this. We have been using a number of different data sets, but this time you're going to use a data set which comes from a rather well-established kind of data set, which is known as the Moon data set. Let me explain this a little bit. In the Moon data set, we got a data set where we wanted to find out if there's a difference in psychiatric hospital admissions rate on full moon nights after controlling for the effect of months. Okay, so every month has got 1, sometimes 2 full moon nights. And here we are only interested in psychiatric hospital admissions. So we are arguing that the psychiatric hospital admissions are higher on full moon nights, but maybe on specific months because of certain seasons in which the admissions are going to be higher. And so what the investigators were interested to do is to find out is this, that from all psychiatric hospital admissions, they wanted to see whether there was an increased risk of hospital admissions before full moon nights, on the day of the full moon night, or after full moon night. But you could equally argue that it's not just a matter of full moon night psychiatric hospital admissions, it may be a matter of the month or the season when that occurs. So to account for that, they also tallied which month that they had this hospital admission in the year 1972. So they took out a span of 1971 to 1972, and then they plotted the hospital admissions of each of these cases. So here is the data. The data is stored in a data file called fullmoon.txt, and we have saved it into the data file called moon data. As we have been doing it for some time now, it's a good idea to start this analysis with a box plot. Why box plot? Because you do realize that in this particular case, we've got an outcome variable, which is measured in scale, which is a continuous variable, an explanatory variable, which is measured in categorical units or factors. Therefore, a natural graphical way of presenting it would be by way of a box plot. The other thing that can be done if you were to use the pairs argument, then you don't get much far because the outcome variable is continuous, the explanatory variable is categorical. Therefore, for each of these categorical variables, you're going to get box plots like sets of boxes. But there is no real simple way in which you can plot two categorical variables. We had seen, though, that there are ways in which you can classify the categorical variables, or you can cross-classify the categorical variables, and you can create a contingency table, and then that contingency table itself would have its own categorical frequency distribution, and those frequency distributions could be plotted using a bar plot, not a histogram, but a bar plot. And that bar plot could give you some sense of the percentages in which the explanatory variables would be occurring within the outcome variables. Now that's always working. That usually works. However, in this particular situation, it's okay for us if we use a continuous variable as an outcome variable and a categorical variable, and then we plot them. The second kind of plot, which is very, very important here, is what is known as an interaction plot. In an interaction plot, we are actually again going to put on the y-axis the continuous variable. In our particular situation, it is psychiatric, or it is psychiatric hospital admissions, total number of psychiatric hospital admissions, or rate of psychiatric hospital admissions. That is, of all the people that could have been admitted, what was the number that actually got admitted. So we got a rate of that at hospital admissions, per day or whatever over the month. And then you have what you say as the particular day in which those people got admitted. So that's another thing. So now we are in a position to say and modify whether, after adjusting for the monthly admission rate, what would be the ranks for the three situations. That is pre full moon night, on full moon night, and post full moon night. And the way to construct that plot would be what is known as an interaction plot. So we would be studying the interactions of those admissions in this point. So let's take a look at the first class of plot, which is a visual inspection of the box plots, and see what we get to see. You can see that there is not much of a difference in terms of people's admission to psychiatric units based on whether that was during the full moon night or after. So maybe after full moon night, before full moon night, or during full moon night. And you can see that that the during full moon night hospital admissions by median was greater, but there was considerable overlap in the three um, moon phase states for psychiatric hospital admission. So not much can be said when we start taking a look at only this bit. On the other hand, if you investigate the box plot for the months of the year in which they got admitted, you can see that there's quite a bit of things that you can say about that it is almost all over the place. Although you can say that in the months of April and May and June there were higher admission rates rather than during the winter months. So season may have played a role, but something that we need to tease out. What these two isolated pieces of information do not tell you is this, that what would be the interaction of these effects. And therefore, this is where the interaction effect shows you something that we have been suspecting all along. We are seeing that during the months of April and June, particularly during the full moon nights, there were higher hospital admissions. And you can see that there is a close mimicking of this, almost like a parallel mimicking of this, for both during, after, and before full moon nights. So the dotted lines are the other kinds of graphs that occur as a result of this. These conceptualizations, that is, effect of the full moon status and effect of the month status on hospital admissions, can be investigated using the two-way ANOVA. So we put the two-way ANOVA here into the picture, and you can see that the admissions of the two-way ANOVA can be modeled using a log of the admissions on the moon and the month. And this is interesting, because what we're trying to do here is this, that we say that this could be a sort of a multiplicative function of the month and the moon. So we say that the admissions could be a factor, sort of a multiplicative factor of the month and the moon. And so we have put together a log function to see how these things work. We could have put a simple admission as well. I mean, that would be okay too. But given the shape of the curve, we thought that maybe a multiplicative effect might be useful, and so we took this. And one of the things that we get to see is this, exactly as we were expecting in the pictures, that the moon phase does not have much of an impact, but you can see that the month has got a very strong impact on the hospital admissions. So that's what we get to see when we compare the ANOVA of this. Now, what is important here is this, that here we have only kept an issue where we have isolatedly or we have added the impact of the month and the moon. So what happens for multiple comparisons, we can use a Tukey's honestly significant difference to see whether there is some impact of whether there are certain months in which these happen. Okay, and we could do it in two ways. We could do one in the moon phase, so that it just makes it a little easier for us to capture. You could also do what is known as the by the month. Let's see what it means. So here we had conducted a multiple comparisons using the Tukey's honestly significant difference, and you see, in order to run the Tukey's honestly significant difference, we'll first have to run the AOV, the analysis of variance. And here you can see that we run the analysis of variance on admissions, month plus moon. Okay. We could also run the admissions of admission probabilities on the log of admissions for month and moon, but we just decided to run this on admissions month plus moon. And then we decided to take a look at the moon phase only. Well, we expect that there is not going to be much of a difference, but nevertheless we could do this. And once you plot the Tukey HSD like that, so you take the AOV or the analysis of variance and do this, you can plot the Tukey diffs too, which is the product which is the object to which this is stored. I leave it to you as an exercise. Use log and mission month plus moon, the original model that we were evaluating, and try this there to see what difference you get. I have not reported it here, but I leave it to you as an exercise. So let's take a look at the Tukey's HSD's test and what do we get to see. As you can see, using the Tukey's HSD tests, you can see that there is not much of a difference in the moon, which was exactly what we've been arguing. You might say that there was not much of a difference. There was a mild borderline difference between during and before, but that's not to say a lot. What you can say instead is this, that there are a lot of overlaps between the before, after, during, after, and during, before. Okay, so this kind of tells you that some of the things that you can do using the two-way analysis. And so what you can do with a two-way analysis is this, that two-way ANOVA, is you can put simultaneously two categorical variables as explanatory variables and a continuous variable as an outcome variable. And you can pretty much read off the charts as the same way that you could read ANOVA. And you can order ANOVA for this, and you can test the significant differences and pairwise comparisons. So this is where we close our the two-way ANOVA bit, because that's how it works. So in conclusion, we can say that there's a whole family of regression equations that you can set up using a very simple notion in R. And that is LM, linear model. We don't need to do anything very complicated. And then you figure out, of course, in this particular case, we did only a continuous outcome variable. And therefore, if you've got a continuous outcome variable and a combination of only continuous explanatory variables, or a combination of both continuous and categorical variables, or a combination of all categorical variables, there are different tools and strategies that you can use. When you have to deal with a continuous outcome variable and a continuous categorical variable, either a single continuous categorical or a single continuous explanatory variable, or combinations of continuous explanatory variables, then you will be using either a simple linear model or simple linear regression or multiple linear regression. When you've got a continuous outcome variable and a combination of a continuous explanatory variable and a categorical explanatory variable, then you will be using what is known as analysis of covariance, or ANCOVA. But in both cases, the basic framing or formulation of the regression model will remain the same. You use the function LM, which is available in the stats package of R. You start with the outcome variable on the left-hand side, then you put a tilde mark, then you put the explanatory variables, specify the data on which you're going to run the analysis, and then you can extract the ANOVA and you can extract the summary information in the same way. But it is up to you to decide what kind of variable that you want to work with. It works very similarly with the analysis of variance as well. In that particular case, you use what is known as an LM, but in this case, you can either have a one-way ANOVA or a two-way ANOVA, and the routine principles are very much the same. You graphically examine the model, then you start taking a look at the regression parameters, summary, and the analysis of variance, and then you start taking a look at, in particular, with one-way and two-way ANOVA with multiple comparisons. In the other cases, you start looking at the outliers and what you can do with the outliers. You can also construct what is known as 95% confidence interval bands along with the interaction plots that are appropriate. So interaction plots are appropriate for ANCOVA and two-way ANOVAs, Otherwise, there are other ways in which you can examine the regression equations. So with this, we complete the two-way analysis of variance. We move next to analysis of longitudinal data, which is quite different from what we've been seeing. Somewhat different, but not a whole lot. There is a concept to learn.
So this kind of completes our tour of setting up linear models in R. We started with bivariate data. Then we talked about simple linear regression where two continuously distributed variables were looked at. Then we we studied multiple linear regression where more than two variables were looked at together at the same time, but both of them were continuous. Then we looked at one continuous outcome variable and one continuous and one categorical variable. That was analysis of covariance. Then we looked at a simple ANOVA, which is also known as one-way ANOVA. And then we looked at one continuous distributed variable and more than one categorical predictor variables. This kinds of gives you a complete set of what you could do if you had to worry only about one continuous outcome variable and a combination of different kinds of predictor variables. So this sort of gave you a sense of what you can do with many different types of situations and what to work with this. In our next module, we're going to do something very different because this time we could allow for a violation of a key assumption of regression. That is, your y variables are not independent of each other. So what do we do? And that is known as longitudinal studies.